You plug in x values, right. So the x values are what? The x values are, let's see here, from 2 to 2 plus h. So there's the 2 and the 2 plus h. So once you have the 2 points, what do? You have y2 minus y1 over what? x2 minus x1. You just do the subtraction. What's going to be in your answer, most likely? You're going to have some h in there somewhere. You're going to have h in there somewhere. So if I picked a value for h, I could now just plug it into there and get a specific average rate of change. Does the algebra make sense? Does the algebra make sense that you're seeing on the board? So let's move on here to fundamental idea of calculus. Oh yeah, that was pretty good right there. That's not bad. Okay, so for the first 2 seconds, this is just slope between 2 points. The slope between time equals 0 and time equals what? Time equals what? 2. The first 2 seconds, right? So here's the first point and here's the second point. Can someone tell me what the equation is for the slope we're going to do? M is going to be what? 2 minus what?
0.
0 over 50 minus what?
0.
Oh wait, we just did 2 minus 0. Do we want to do that? No, why not, Mikey? Yeah, you know, theoretically we could arbitrarily choose to do everything in the reverse, but we shouldn't do that because if we did that, we'd have time per feet, and we don't really like that, right? So what should we do instead, Sarah?
We should always make time the independent factor.
Yes, correct. Over 2 minus 0. So what do we get here? 50 over 2, which is 25, and it's going to be, what is it, feet per second? So that's what the car, what is the car's average velocity? And that should make sense because how fast is the car going at the beginning here at time equals 0?
30.
So if it's slowing down, should we get a number less than
Yes.
30? Yes, we should. What is the car's average velocity over the second 2 seconds? So that's 2 to 4. So that's going to be 76 minus what?
50.
Minus 50 over
40 minus 2.
4 minus 2.
Oh,
That's fine. So it's 26 over 2, which is
13 per second.
13 feet per second. Now, here's a question. This is fun. How fast is the car going at 2 seconds? How fast is the car going at 2 seconds? Now, this right here is something we were leading towards figuring out at the last class, which we didn't do. This is another way of, this is asking, what's the instantaneous? And we haven't talked about this yet, so it's a little bit new. Instantaneous rate of change. Any ideas about how to figure that out based on these values right here? Any idea how to figure this out? Yeah, Caleb. What can we figure out?
So don't you want to...
So that's from there to there, but you said do it in the front and do it from here to there.
Yeah.
So if you did it from, we'll call this M2 right here, what's that going to be? M2 is going to be 4 over...
Or minus...
Sorry, yeah, I got to actually do the subtraction, right? 59.4 minus 50 over
2.5 minus 2.
exactly. So you have 9.4 over, so what's that going to be? 18.8. Okay, so the average rate of change from here to here is this. The average rate of change from here to there is that. So what could you do with those two numbers? If you wanted to know what the average rate of change was at that specific instant, here's the average rate of change here. Here's the average rate of change here. What could you do with these two numbers? One way to do this is then to take the average. It's somewhere probably in between. Now here's the thing.
These points are kind of far apart, so you don't know.
Exactly, and that's all relative, right? Like far and close, hot and cold, it's all relative. So we'll get to that in a second, right?
Yeah.
So theoretically, the closer the points are, the better this estimate will be. But given 2 points that are on either side, generally speaking, a good thing to do would be to average these two things. So you get M1 plus M2 over 2. So that's going to be 21.2 plus 18.8 all over 2. So that's going to be what? 40, right? Is that nicely 40?
Yeah. Yes.
40 over 2, so 20. And then what was that, feet per second? Feet per meter, what is it, feet per second?
Yes.
Feet per second, nice. It's always a nice thing, generally speaking, when that happens, when you get nice numbers. You know, it's kind of cool. So what Caleb pointed out, though, is that these points, like this time distance, 0.5 to 2, is a relatively large amount of time. Meaning, if you wanted this to be more accurate, if you wanted this average rate of change to be more accurate, it would be nice if we had more data. What data would we like? We'd love to know at like time 2.4, where is it? And at time 2.6, where is it, right? Because the closer you are, the more accurate this estimate is going to be.
Closer to like, so you mean like 1.9?
Oh, is it at 2? I'm sorry, was it? Yes, I'm sorry. 1.9 and 2.1. I was looking at the wrong ones, yeah. So if you looked at this graphically, what does this look like? Well, I'm not going to do this perfectly, but let's say this is the function. So this is going to be time, and this is distance from what? Was it from stopping point? From breaking point, is that what they call it?
Yeah.
Breaking from, so you start here, and it's slowing down. It's like this. Let's say that's what it is. If I asked you for the average rate of change at this point, you're looking for what is the instantaneous rate of change at that point, which is the slope of the tangent line, which we haven't figured out how to do exactly yet. But if I take this slope right here, let's say this is right before to here, and then I take and call that M1, and then I take this slope right here and call that M2, the slope we're looking for is the slope of the tangent line, right? It's from like, it's like this. I wanted that to be red. It's like this. So if we were to average, not supposed to be a straight line, if we were to average M1 and M2, does that feel like it's a okay way to estimate what we're trying to find? How does it feel? Does it feel okay? I keep on erasing the wrong one. Do you agree? I'm just trying to make this flat. I'll do it like this instead. This is supposed to be a line like this. But do you see exactly what we're trying to do there? There is a different way to do it. There are actually several ways to do it, but right now this is the best we can do, because do we have any idea what this function actually is right here? No, we don't have any idea what the function actually is. All we know is what we're given, and this is the best we can do with what we're given.
How many distance, I guess, in feet over a certain amount of time, and the interval.
Well, it represents the average rate of change between those 2 points, right?
Yeah.
So what can you tell me about the average rate of change between these points? What's going on? The ARC is what? ARC is decreasing. The ARC is decreasing. So therefore, what has to be true? The car is slowing down. The average rate of change is decreasing, so it's slowing down. Okay, so if we generalize this, so let's say we have these 2 points right here, and we want to know what the average rate of change is right here. If we wanted to know what the average rate of change is right there, let's just call this f of x, this function. This function is f of x. If you want to find the average rate of change from a to a plus h, what's the first thing you need to find? What did we do first? What do you have to find? No, we're not finding a. A is going to be set. A is that x value, and a plus h is another x value. What do you need to do to find the average rate of change between 2 points? What do you find? We need the y values first. We need the y values because the average rate of change is just the slope between 2 points. So we have f of a plus h. That's the other y value. And what's the other one? F of a. What I'm saying is this right here is, that height represents f of a, and this height right here represents what? F of a plus h. Exactly. So if we want to find the slope between those 2 points, what is that slope going to be? F of, so the 2 points, I'll make this more explicit. The point we're going to is a plus h, comma what? F of a plus h. What's the second point, or what's the first point? A, comma, f of a. So what's that slope going to be equal to? F of a plus h minus f of a all over a plus h minus what? Does that simplify it all?
Yes.
Yeah, so m is equal to, what is m? So I'll put the m there. What cancels there? The a on the bottom. So you have f of a plus h minus f of a all over what? H. So that right there is the average rate of change between those 2 points. Let's go back to this table though. When we did this table, we had the average. We averaged 2 average rates of change, the one right before and the one right after. What was the way we could make our estimate better for the instantaneous rate of change? What did I say we'd want theoretically? We'd love it to get closer, right? What's this gap from 2 to 1.5? That's half a second, right? What's this one? We would love that to be really, really, really small, right? As this gets smaller, this overall average will get closer and closer to the actual rate of change. As this gets smaller, And let's just look at one side here. Let's look at one side here. As this gets smaller. So on this equation right here, which one do we want to be really small right here? What value do we want to be really, really small? A is fixed. Which one do we want to be really small? We want h to be really small. H represents the distance from where we want the average rate of change. H represents the distance from where we want to calculate the average rate of change. So we want h to be really, really small. We, in fact, this equation right here gets closer and closer and closer to the actual average rate of instantaneous rate of change as h goes to what? 0. As h goes to 0. As h goes to 0. So what equation are we going to see over and over again? We're going to see this. We're going to see f of a plus h minus f of a. What's on the bottom? But what goes out front? The limit as? There's no x in there, kids. H goes to 0. We are going to do limits where h goes to 0 of this difference quotient right here. This right here. This right here represents, this limit is exactly the instantaneous rate of change. But in order to use this, we need a few things. We'd need, what do we need if we're going to use this? If we wanted to find an actual value, what are we going to need? We're going to need the function. B, we're going to need the a value, right? You need a function and where we're trying to find the instantaneous rate of change. Without the function, we can't do this exactly. With a table, we can only use the closest points we have. And I like doing the average method. Some people just use the beginning, but the average method gives you an idea of the trend. Is it slowing down? Is it speeding up? Like if we just used, on this one right here, if we just use this one, like it was 21.2 and it went to what, 18. So it's slowing down, right? So we know it's probably going to be less than 21.2. If we didn't use the 18.8, the best we could do would be around 21.2. We don't know which direction it's going or how fast the average rate of change is changing. Because we did one before and after, we have an idea. Here, if we have the function and we have an a value, we can do this exactly. Assuming we can solve the limit. Are we going to be able to solve all limits? No, we're not going to be able to solve all of them. You are going to see this over and over and over. So if we find our y values, we're going to need to do f of 3, which is 2 to the third, and f of 2, which is 2 squared. So that's 8 and 4. So what are the points we're dealing with here? 3, 8, and what? 2, 2. So what's the average rate of change going to be? Someone who hasn't spoken yet. 2, 4. Thank you. What's the average rate of change slope going to be? Can someone who hasn't spoken yet tell me? Liv.
4 minus 8.
Go from where we're ending up. 8 minus
4
over.
3 minus 2.
I would prefer this, right? So it's 4 over 1. What are the units there? So it's going to be equal to 4 what? 4 what? 4 feet per second. 4 feet per second. 4 feet per second. Is that a real? By just a side question, is that a realistic walking speed?
No.
That's a 4 feet per second.
Yeah,
That's a real. Like think about it. Like 1 second, 4 feet. Yeah, that's a realistic walking speed. Okay. Estimate his instantaneous velocity at t equals 3. Estimate the instantaneous velocity at t equals 3. Now, how could you estimate the instantaneous velocity? We're talking about maybe 2 values right now you could do. And you need an x value, these 2 x values. So at the center here, you want it at, so this is time and f of t. F of t, like this. What 2 times do you want to compute? What 2 times? Closest thing. Okay, so what numbers? Give me some numbers.
Like
2.9.
2.9 and what? 3.1. Use your calculators and tell me what this is. Tell me what it is.